Okay, so today's lecture is going to be dedicated to doing review for exam 2. That's midterm 2, which takes place next week. All right, so the first question is what material is going to be on exam 2? So let's just review a little bit. So we had exam 1, which covered weeks 1 through 5. I'm not going to ask you questions which is directly coming from those particular lectures, weeks 1 through 5. However, obviously, you need to know a lot of that material in order to understand the later material. Okay, so now weeks 1 through 5, okay, and then we had week 6. Week 6 was the week where the university shut down due to the inclement weather. So nothing was covered week 6. So it would start at week 7. Now week 8, we had the first midterm. I believe that we did the review on Tuesday and then the midterm on Thursday. So there wasn't any new material in week 8. So the midterm 2 is going to cover, I'll just say weeks 7 through 11, although week 8 was the midterm. Week 6 was canceled. So it does not cover the March 30th lecture, which was week 12. All right, roughly speaking, this started with the stuff about the TNB, the kappa, the curvature, and the oscillating and normal planes. That's where what we were doing right after week 5. And that starts on February 23rd's lecture, just in case you're not keeping track of the weeks. And then the last lecture, so we went through functions of several variables, partial derivatives, things like that. And then that ends on March 25th lecture. And I think the last thing we covered was, it was in the section where we were doing directional derivatives and the gradient. Okay, but those are the exact dates, February 23rd through March 25th. Now, as usual, there's a lot of material that will be, covered on this exam. So with just one lecture, it's impossible to go over everything. What I'll do is I'll just highlight some of the main things. Now, I was pretty generous on the first review. I was pretty generous in general about exam 1. I'm not going to be as generous on exam 2. Okay, I think I was a little bit too generous on exam 1, basically all aspects of it. So I'm going to be a little bit less generous on exam 2. So it's going to be a little bit more challenging. I'm not going to give you 2 hours this time. I'll just give you the regular class time. And this review, it's not going to be as generous as the first review. So the first review for exam 1, I basically did a problem corresponding to almost every exam question. I didn't do every exam question, but most of the exam questions, I did something very similar to that in the review. I'm not going to do that so much this time. Okay, so it will be a very useful review, what I'm going over today. But don't expect that the exam is going to line up problem by problem with what I go over today in this review. Okay, so let me then begin. And I'll just do it chronologically. I'm not going to have a lot of time for discussion because I have to cover all those weeks in today's lecture. So let's see. So we started with, or I shouldn't say we started with, but today's lecture we will start with the TNB functions. So the context here is that you have a vector function r of t, and then associated with r, we have these functions t and b, which are defined as follows. So t, that's called the unit tangent. It's just the basically r prime, the derivative or the velocity, but the unit vector. Then we had n, which is the unit normal, which is the derivative of the unit tangent, but the unit vector, the normalization. And then we have b, the binormal, which is the cross product of t and n. So all three of these vector functions, at any given t, they are orthogonal to each other. So like they form like a three-dimensional coordinate system, so to speak. And they have unit length. Okay, and then we have the curvature function. The definition was the derivative of the unit tangent with respect to arc length, the length of it. But we have this other useful formula. So it is the length of t prime over the length of the derivative of r. Okay, and then associated with these objects, we have the osculating plane and the normal plane. So the osculating plane, and these are functions of t, right? So it would change depending on what t is. So it's the plane which contains the vectors, these orthogonal vectors, t and n. And the normal plane is the plane containing the vectors n and b. Now there's another useful way to describe these two planes because let's see, what do we know about these planes? They both contain the point corresponding to RT. And because, let's say the osculating plane, because it contains T and N, the binormal B, which is orthogonal to T and N, will be orthogonal to that plane. And similarly, the normal plane will contain the point corresponding to RT. And because it contains these N and B, and the vector T is orthogonal to N and B, it can be described as, the normal plane can be described as the plane containing RT, which is orthogonal to T. Because we know when we're trying to describe planes, the equation that we use is described using a point on it and a vector orthogonal to it. So that's a very useful description of the osculating and normal plane. Osculating plane, which contains RT and is orthogonal to B, and similarly, the normal plane is the plane which contains RT, and is orthogonal to T. Okay, so let's actually calculate these different objects in a particular example. So we will consider the helix. All right, so let's begin. So T is equal to R prime over the length of R prime. So let's calculate those objects. R prime minus sine Ti plus cosine Tj plus K. And the length of R prime minus sine T squared plus cosine T squared plus 1 squared. Sine squared plus cosine squared is 1. So square root of 2. All right, so T is going to be R prime times 1 over square root of 2, or okay, so that's T, the unit tangent. So N is going to be T prime over the length of T prime. So let's calculate T prime. And the derivative of a constant is 0. And the length of T prime, okay, so sine squared plus cosine squared is 1. And then pull out the 1 over root 2. So if you factor out the 1 over root 2 squared, then it's that times cosine squared plus sine squared, which becomes 1 over square root of 2. Okay, so N T prime over length T prime okay, so we're dividing by 1 over square root of 2, which is the same as multiplying by square root of 2. So we would get minus cosine T like that. Or I could just write it like this without the parenthesis. All right, so that's N. And then the binormal would be T cross N, which is the determinant, IJK. And then let's see, the row of, second row would be T. And the third row would be N. Okay, let's see. So there's going to be I, this cosine thing times 0 is 0, minus negative sine t over root 2, double minus is positive, minus, then the j1, similarly the sine t over root 2 times 0, which is 0, minus negative, which becomes plus cosine t over root 2, and then the k, sine squared t over root 2, minus negative cosine squared t over root 2. So this, if you factor out the 1 over root 2, it'd be times sine squared plus cosine squared, which is 1. So I'm making 1 over root 2. Let's just write it without parentheses. Okay. Let's calculate the curvature kappa. So the formula that we usually use for kappa would be the length of t prime over the length of r prime. And the length of t prime was 1 over root 2. The length of r prime was root 2. So that's the same as saying 1 over root 2 times 1 over root 2, which is 1/2. All right, so we calculated T and B and kappa, which is a lot of work. Now let's calculate the osculating normal planes of the helix at a particular point, 0, 1, pi over 2. So this point 0, 1, pi over 2 is supposed to be a point on the curve, which is being traced out by the helix function. And the helix function is given by, cosine plus sine plus tk. Okay, so the value of t for which this vector is at this location, it's usually easy to figure out. It's really easy in this particular problem because the third coordinate is t, and then the third coordinate here is pi over 2, so t must be equal to pi over 2. And you can double check that by plugging in pi over 2 into cosine, which would be 0, and pi over 2 for sine, which would give 1. So this point here corresponds to when t equals pi over 2. Okay, so let's see. The osculating plane is going to contain that point. Okay, why is my cat meowing? So the osculating plane contains this point, and it's supposed to be orthogonal to the b vector. So we're going to need to calculate b at t equal pi over 2. So let's see, what was b? All right, so we're going to plug in t equals pi over 2. So the first component will be 1 over root 2. The second one is 0. Cosine pi over 2 is 0. And the third one is 1 over root 2. So again, that's 1 over root 2 on both the I and k component. All right, so the osculating plane is the plane which contains this point and is orthogonal to this vector here. So therefore, its equation, if you just remember from chapter 12, and then simplify it. No, I did something wrong, sorry. Root 2 times 2. All right, can we simplify this? Yeah, if we multiply everything by root 2, so this answer is okay. If you want to be really picky, multiply by root 2 and get this. Or if you're really picky, solve for z. So any of those answers would be okay. So that's the equation for the osculating plane. Okay, similarly, the normal plane will be the plane which contains the point 0, 1 pi over 2 and is orthogonal to t. And this is at t equal, lowercase t equal pi over 2. All right, so we're going to calculate t pi over 2. I'll have to remember what t is. Okay, let me just write down t for reference here. And we'll plug in lowercase t equal pi over 2. All right, so that's minus 1 over root 2i. Cosine pi over 2 is 0. 1 over root 2k. Okay, so therefore the normal plane equation, using the standard equation for a plane, actually let me write this as in vector form. All right, so it's going to be minus 1 over root 2 x minus, I got to remind myself of the point we're looking at, which is 0, 1 pi over 2. Simplify it. And again, that's an okay answer. You could also make it a little simpler, multiply by root 2. Or even solve for z. So any of these three equations is a good enough answer. Okay. All right. So yeah, so that kind of problem, it is kind of a lengthy question. If I did ask a question like this, you would have to be pretty on top of the material to do that in a reasonable time. All right, so let me move on to the next topic, which is going to be these issues with, the study of motion, because sometimes a vector function can be interpreted as the path that a particle is taking in space, corresponding to different times. So we can think of a vector function as a position function of a particle. And then we have these natural interpretations of the derivatives of the vector function. R prime would be velocity, denoted v. That's like the instantaneous velocity of the particle at a particular time. And the second derivative of r, which is the first derivative of the velocity, is acceleration. And then we also have speed, which is the length of the velocity. Okay, let's do a quick example of computing these things. So let's say that our position function is given to us, ti plus t squared j plus 2k. All right, so the velocity is going to be the derivative, which will be I plus 2tj plus 0k. The acceleration is the derivative of the velocity, which is 0I plus 2j. And then the speed is the length of the velocity, square root of 1 squared plus 2t squared, which is 4t squared plus 1, square root of 4t squared plus 1. So let's say at a particular time, say t is equal to 1. Let's compute these things for that particular time. All right, so the position at time 1 is this vector position here. The velocity at time 1, let me write it as vectors. So the velocity would be, let's see, so it's I plus 2tj. So I plus 2j, or 1, 2, 0. The acceleration at time 1, 2j. So the acceleration is constant. The acceleration does not change. And the speed at time 1, 4 1 squared plus 1, or square root of 5. All right, so that kind of question is pretty straightforward. There's another kind of question which is a little bit more tricky, which involves integration. I'll just mention this briefly. If you are given some information about r in terms of its velocity, you can sometimes figure out what the position function is. So if you know the velocity and also you know the position at some particular time, just one data point, one particular value of the position function. So we can find R when that information is given. And the formula for that is the position function is equal to the position at time t0 plus the integral from t0 to t of the derivative of r, which in other words, the velocity. And the reason that's true is this is simply the fundamental theorem of calculus. If you write it a little differently, if you write RT minus RT0, that is exactly the definite integral of from T0 to T of R prime. That's exactly the fundamental theorem of calculus, that statement. Now this formula is true for any vector function R. So in particular, if you apply this formula to the case where you let R be a velocity function of some other function, that would say you can integrate the acceleration to get the velocity. So a little bit more complicated question was, you can find R if you know the acceleration of R together with some particular value of R and the velocity. Because then you can solve for R in two steps. First, you would solve for V using this formula. And then now that you know V, you can, in the second step, go back and find R using this formula again. Okay, so that covers a lot of stuff about these vector functions. I'm now going to move on to functions of several variables. All right, so we had functions of several variables. What does that mean? We had a discussion about taking limits and continuity. So let's start with some of those topics. And I'll just do a few examples. All right, so for example, let's take the limit as xy approaches 2 minus 1 of the function x squared y plus xy squared over x squared minus y squared. All right, so this thing right here is like our function of two variables. Now, this function is a rational function. It's a ratio of two polynomials. Polynomials are always continuous, and a rational function is going to be continuous at the places where the denominator is not equal to 0. Now in this case, the denominator is x squared minus y squared. That's going to be equal to 0 if x is equal to plus or minus y. Now, we're taking the limit as we approach the point 2 minus 1, which is not one of the points for which x squared minus y squared is equal to 0. All right, so this is going to be a continuous function, at least if you're close enough to 2 minus 1. So to take this limit, we just apply continuity. of the numerator and the denominator. So the limit is going to be equal to just substituting in x equals 2, y equals minus 1. So we get minus 4 plus 2 over 4 minus 1 minus 2 over 3 minus 2/3. All right, so that problem was kind of easy due to the fact that we could use continuity to take the limit. So let's look at another example where we're not going to have that situation. So we're going to take the limit as xy approaches 0, 0, or attempt to take the limit, I should say, because it's going to turn out the limit does not exist. Of this particular function here. So let's see why we cannot do exactly the same thing we did in the previous problem. The denominator is going to be equal to 0 when x equals 0, y equals 0. Okay, so this function, which is a ratio, is not going to be continuous at 0, 0. If it were, we would just apply continuity and plug in 0, 0 in here for x and y. So when you can't use continuity like that, you may not necessarily know immediately whether the limit exists or not. So the standard test for checking that it does not exist is to consider different paths towards our point, in this case 0, 0. Because if the limit does exist, then the limit's going to be the same no matter how you approach the point 0, 0. And there's only a few kind of standard things you'll see in this course. There's only a few standard paths that you would consider. I think in the homework, we considered the path along each axis. And the other natural paths to take are the paths along the lines x equals y and x equals minus y. A little bit more generally, you could consider paths approaching your point along straight lines, because straight lines are easy to express, like say y is equal to 2x, for example. So my suggestion is for doing these kinds of problems is to try a couple of different pairs of lines approaching your point, starting with the x and the y axes, then the lines y equals x, y equals minus x. If those limits are all the same, and by the way, then you could also consider like a mix of those, like you can consider like the x-axis versus y equals x line. So those 4 lines is probably enough to answer your question. Now, if you check so many different pairs and you're always getting the same limit, that would suggest that the limit, maybe it does exist. But you can never verify that by just checking a couple of paths to your point. You would have to give a more algebraic argument. So the examples we did in lecture, what we did was we used the squeeze theorem. So we proved like the absolute value of our function was somewhere in between, in the examples we looked at, it was like between 0 and the absolute value of x, or between 0 and the absolute value of y. And because as you approach the point 0, 0, the left side and the right side go to 0, the squeeze lemma or the squeeze theorem implies that the function in between has to go to 0 as well. All right, that's sort of a general discussion of how to approach these problems. This one's going to be kind of straightforward. We're just going to consider the two axes, the x-axis and the y-axis. So we're going to consider two different paths of approaching our point, 0, 0. So let's see. So if we approach 0, 0 along the x-axis, on the x-axis, y is equal to 0. And because we're never going to consider the point 0, 0 itself, x would have to be not 0. So in that case, what does this function simplify to? All right, so y is equal to 0, so it disappears. So for any x and y on the x-axis, or for any point x, y on the x-axis, this function we're taking the limit of is just going to simplify to x squared, which approaches 0 as xy approaches 0. As xy approaches 0, 0. All right, so along that path, our function is approaching 0. Let's see what happens when we approach the origin 0, 0 from the y-axis. So along the y-axis, it's the x which is 0. And since we never consider the point 0, 0 itself, y will be not equal to 0. Okay, in that case, our function is going to simplify. The x goes to 0, so it disappears. Okay, the y squared cancels, and you're left with minus 2. Okay, so in other words, for all points on the y-axis other than the origin, this function is equal to minus 2. It's constant. So therefore, this function would have to approach that constant value, obviously, because it never changes. Okay, so what happens along the y-axis is our function is constant. It's constant minus 2, which means it's approaching a different value than it approached along the x-axis, where it approached 0. So therefore, this limit does not exist. So since we get two different limits along two different paths, the limit does not exist. Okay, the next topic is going to be partial differentiation, and this is an extremely important topic, possibly the single most important topic of this course. It's going to be used for almost everything we do from this time it's introduced until the end of the semester. Luckily, partial derivatives are pretty easy to calculate. So let's just do a simple example to review the general idea. So when you calculate the partial derivative of f with respect to x, which can be written in either of these two ways, fx or del f del x, What you do is you treat the other variable, in this case y, as a constant. You just pretend it's a constant. So therefore y squared would be a constant, and we're just taking the derivative of e to the minus x, which is minus e to the minus x, or minus y squared e to the minus x. If we take the derivative of f with respect to y, then we do the opposite. We treat the variable x as though it were a constant. And then the partial derivative. So with respect to y, e to the minus x is a constant, and the derivative of y squared is 2y. So the answer is 2y e to the minus x. Okay, and you do the same thing for any number of variables. If you have a function of 3 variables, x, y, and z, and you take the partial derivative, say, with respect to y, then you treat the other 2 variables, in that case x and z, as if they were constants, and apply the same kind of rule. Okay, so let's do an example with implicit differentiation. So if you think of like this example right here, just to motivate what we're about to do, a related idea to a function of 2 variables is the graph of it, which is when you say z equals y squared e to the minus x. That's a surface in 3-dimensional space. So z is a function of x and y. So if you wrote z equals y squared e to the minus x, you're given an explicit description of z as a function of x and y, because it says z is exactly equal to this function that we wrote down. Now sometimes you don't have that luxury of being given the function explicitly, but instead you're just given an implicit description of z, which is an equation which relates the variables x, y, and z. Sorry, I'm having trouble spelling for some reason. Implicit differentiation. All right, so let's do an example like that. So when you're given an equation like this, you think of z as a function of the other 2 variables. It's just not given explicitly. So the equation is an implicit description of z as a function of x and y. So let's calculate the partial derivative of z with respect to x. So what you do is you just take both sides of the equation and take the partial derivative with respect to x. So the partial derivative of the left side is going to be 2x minus 0. Okay, so how do you handle z? Well, z is a function of x and y. So we're basically using the chain rule, 2z del z del x minus 2 del z del x. So whenever you take the derivative of anything involving z, you have to use the chain rule. So you take the derivative of the outside function, in this case z squared would be 2z, but you have to multiply by del z del x. Okay, the right side of the equation, the partial with respect to z, that's just a constant, so it's 0. And then we'll solve for del z del x. So you can factor out the del z del x each time it appears. And we could simplify this by canceling the 2. That's probably better to get this. All right, so remember this particular section or lecture involving partial derivatives. I gave the definitions, the formal definitions of the partial derivatives, how to compute partial derivatives, which we just covered briefly. Then we interpreted the geometric meaning of partial derivatives, and that was when you have the graph of the function and you intersect the graph of the function with those vertical planes corresponding to a fixed value of x and a fixed value of y. That intersection is going to be a curve, and then the tangent line is going to have slope equal to the partial derivative. Okay, that stuff was important. We covered implicit differentiation. And then the last thing was these higher order derivatives, where you take a derivative, a partial derivative, which gives you another function, let's say of x and y. So you start with f of xy. If you take del f del x or del f del y, that is also a function of x and y. So you can then take the partial derivative of that again. Then we had that notation for these higher order partial derivatives, which you have to be familiar with. Then we had this important theorem, which basically said that the mixed partial derivatives are equal. And this was called Clairaut's theorem. Which said that assuming that your second order partial derivatives exist and are continuous, then they have to be equal. So it doesn't matter the order in which you take the partial derivatives. If you have a function f of xy, you could take its derivative with respect to x and then take the derivative of that function with respect to y. You're always going to get the same thing as if you had done it in the opposite order, first taking the partial with respect to y and then the partial with respect to x. I hope I said that correctly. So if you take the partial with respect to x, then y, that's the same as if you took the partial with respect to y, then x. And the same thing is true in higher order. Like if you had del 3f and then some combination, just inductively, it would follow from Clairaut's theorem that those mixed partial derivatives are equal as well. Okay, so let's move on to the tangent plane. Okay, so the idea is that we're looking at a function f of x, y of two variables, and we look at the graph of the function, which is the surface z equals f of x, y. Now, if you suppose that we have a point on the graph, that means it's of the form a, b, f, a, b. we can use the partial derivatives to describe the plane which is tangent to the surface, the graph of f, at this point AB, FAB. And the equation for the plane is as follows. Okay. If you solve for z in this equation, that's going to give you what's called the linearization of f. So that would be a function of two variables, L of xy, where L of xy is just solving for z. Now, to explain what that means, we realize that this tangent plane, described by this equation, is approximating the graph of f near this particular point, AB, FAB. So basically, this plane is the best linear approximation of the surface. So therefore, because the surface, which is the graph of f, the z-coordinate of the points on the surface correspond to the values of the function f. So we can think of the same thing as the tangent plane as being the graph of some function. And since the tangent plane approximates the graph of f, the function, whose graph is that surface, approximates the function f. So L of xy is an approximation of the function f near the point AB. And therefore we could write the linear approximation of f like this. Okay, let's do an example of computing these things. So let's consider a particular function, which is f of xy equals 2x squared plus y squared. And in this case, we are interested in a particular point, 1, 1. Okay, so the graph of this function would be described by the equation z equals 2x squared plus y squared. So let's write down the equation for the tangent plane of f at this point. So we calculate the partial derivatives of f. And let's calculate the value of f at 1, 1, which is 2, 1 squared plus 1 squared, or 3. Okay, so the point on the graph of f that we're interested in is 1, 1, 3. Okay, so therefore the tangent plane, using the equation above, the plane which is tangent to the graph of f at the point 1, 1, 3 is z minus 3 del f del x, which is 4 x minus 1, plus del f del y, which is 2 y minus 1. Okay, and then if we solve for z here, what do we get? Well, this is the equation for the tangent plane. And therefore the linearization of f is the function which is z. So L of xy would be 4x plus 2y minus 3. Okay, let's move on to the chain rule. So the chain rule took several different forms because there were different types of situations we were looking at, but there was one general chain rule. All right, so let's look at the different instances of the chain rule. So let's say z is a function of x and y, and x and y are functions of a single variable t. So in that case, dz dt is del z del x dx dt plus del z del y dy dt. Then we have this tree diagram. So you have the variable z at the top. It's a function of two variables, x and y. X and y are functions of t. So we can take the partial with respect to x and y of z. So we label that particular branch of the tree with those partial derivatives. And then x and y are functions of t, so they have the ordinary derivatives, dx dt, dy dt. And the idea is the chain rule is obtained by taking each path from z to t, multiplying these derivatives, and then adding. Okay, that's kind of the first case. The second case is when those variables x and y are themselves functions of several variables. Okay, so this is like the first case. So let's say z is a function of x and y, but now x and y are functions of two variables, s and t. Okay, then the chain rule is going to say del z del s equals del z del x times del x del s plus del z del y times del y del s. And the same with the other variable, t, del z del t, del z del x del t, plus del z del y del t. Okay, in this case, the tree diagram would look like you have z at the top. It's a function of two variables, x and y. But now x and y are functions of two variables themselves. So we can label these lines with the derivatives, del z del x, del z del y, del x del s, del x del t, del y del s, del y del t. And then if we want to take the partial derivative of z with respect to s, we would take each path from z to s. There's two paths like this. Multiply the derivatives along the paths and add. And then we get exactly this. And same thing with t. Okay, the most general chain rule that we're going to consider in this class is when we have z is a function of some number of variables, some finite number of variables, and each of those variables is a function of, say, m many variables. Let's see, what do I want to call this? Let's just say u1 through um. Then for each of these u variables, we can take del z del ui, and that's going to be del z del x1, del x1 del ui, del z del x2, del x2 del ui. That was an I right there, sorry. Del ui up to the final variable xn, del z del xn, del xn del ui. And the way to remember this, besides the tree diagram, the first factor in each of these summons is going to be corresponding to the variables which z is a function of, x1 through xn. And then the second factor is always going to be taken with respect to the desired variable, which is ui. See, all of these are ui's here. So you take the partial of each of the variables with respect to ui. Okay, in the tree diagram, I'm not going to draw the whole thing, but it would be similar. You have z as a function of x1 through xn. And each of these variables, in turn, is a function of u1 through um. And then you can label each of those lines with the corresponding appropriate derivative. And then if you want to take the partial derivative of z with respect to a particular variable, you would just take all the paths starting from z and leading down to that variable, multiply each derivative along each such path, and then add them together, and you get exactly this formula here. Okay, so let's just do one example of the most general form. So let's say z is equal to x to the 4 plus x squared y. And in turn, x is a function of three variables, s, t, and u. X is s plus 2t plus u. And y is also a function of stu, s times t times u squared. Okay. Let's take the partial derivative of z with respect to t at the particular point s equals 4, t equals 2, u equals 1. Okay, so let's write down what is del z del t in terms of its general formula. So we'll have there's two variables, right? Z is a function of x and y. So it's going to be del z del x, del z del y, and then times del x del t, del y del t. Then we have to evaluate these at the appropriate point. All right, so let's calculate del z del x. 4x cubed plus 2xy. Del z del y would be x squared. Del x del t. All right, so x is s. Hold on a second. Okay, so x is s plus 2t plus u. The partial with respect to t is just 2. Del y del t. So y is equal to stu squared. So we treat s and t as constants. Excuse me, we treat s and u as constants. And that's times t, so it's going to be su squared. All right, then finally we're going to take del z del t at 4, 2, 1. That means s equals 4, y equals 2, u equals 1. All right, so that's going to be del z del x, which is 4x cubed plus 2xy, times del x del t, which is 2, plus del z del y, which is x squared, times del y del t, which is su squared. And we're evaluating this whole thing at 4, 2, 1. Now x and y are appearing in this formula, and they themselves are functions of s, t, and u. So we would actually be good to compute x and y separately at those locations, 4, 2, 1. All right, so s plus 2t plus u. Sorry, I didn't do this in the best order. Let me write down what x and y are again. S plus 2t plus u. And y is stu squared. But I could just write it down here. So x at 4, 2, 1 is 4 plus 2 times 2 plus 1, which is 9. Y at 4, 2, 1 is 4 times 2 times 1 squared, which is 8. Okay, plug in those values for x and y here in del z del t. Okay, so that's going to be 4 times 9 cubed plus 2 times 9 times 8 times 2 plus 9 squared times s times u squared, which is 2 times 1 squared. Okay, so then if you enter that in a calculator or do it by hand, you'll get 6444. All right, so that's an example of using the chain rule. Okay, and then the last thing we covered was this material about the directional derivative and the gradient. So the general idea of the directional derivative is that it's just a generalization of partial derivatives. You think of partial derivatives as giving the slope of the tangent line in two specific directions, the x-axis direction or the y-axis direction. If you look at the graph of a function f of xy, instead of just looking at those two directions, you could look at any possible direction and intersect the graph of the function with the vertical plane going in that direction. And then that would give you a curve, and the slope of the tangent line would be the directional derivative. Okay, the directional derivative is denoted with this notation duf at a particular point. And then we have this theorem which says if you're given a function f of xy in a direction u, which is always going to be a unit vector, then the directional derivative of the directional derivative of f in the direction u is del f del x a plus del f del y b. Okay, we actually gave the proof of that in lecture, which wasn't that hard. So let's do an example. Let's find the directional derivative of f at 0, 1, where f is the function y times cosine xy, and u is the vector which makes angle pi over 4 with the positive x-axis. Now the directional derivative, you're always going to take it in the direction of a unit vector. Okay, so u is going to be equal to cosine theta sine theta. In this case, theta is pi over 4, which means the components of u are root 2 over 2. Let's calculate the partial derivatives of f, del f del x. There y is a constant, so that's minus y sine xy times y, or minus y squared sine xy, and del f del y. There x is constant, so we're going to use the product rule. And let's calculate these partial derivatives at the point of interest, 0, 1. So that's going to be 0. And del f del y at 0, 1. Cosine 0 minus 1 times sine 0 times 1. Sine 0 is 0. So we just get cosine 0, which is 1. Okay, so using the formula above, this directional derivative is going to be del f del x at 0, 1 times a. In this case, a, this is this vector up here. So this is a and b. A and b are both root 2 over 2. Plus del f del y at 0, 1, root 2 over 2. So that's 0 times root 2 over 2 plus 1 times root 2 over 2, which gives root 2 over 2. Okay, and then the last topic was the gradient. This is a very important topic which can be thought of from all sorts of different angles. For the current lecture, or the current topic, we're relating it to the directional derivative because it spills out from that formula. So the gradient of a function f, which is written with this upside down triangle, the gradient of f would be the function, the vector function whose components are the partial derivatives of f. And then the main point in connecting this idea with the directional derivative would be that the directional derivative, it's just another way of saying the same thing. The directional derivative of f in the direction u is the dot product of the gradient with u. Right, and that's just because of that previous formula. Where u is ab. Okay, it's just immediate from this formula, right? So usually when you're asked to compute the directional derivative of some given function, you will calculate, as a step in solving that, you would calculate the gradient. So you'd calculate the gradient of f and then take its dot product with the direction u. Okay, so that's basically what I wanted to cover. I recommend you still carefully review your notes and all the examples we did in class. And the purpose of this review was just kind of to focus on some important examples, important ideas. But you shouldn't rely completely on this, this review. Some of the questions are going to cover things which we didn't quite cover directly anyway in today's review.